Okay, let me welcome all of you back to another session of organic chemistry. In today's session, we are going to conclude our discussion on chapter 21. If you recall, when we left on Tuesday, we started our discussion on the synthesis and nomenclature of carboxylic acid and carboxylic acid derivatives. So we are going to conclude on those topics today and then discuss the nucleophilic acid substitution reactions with regard to carboxylic acid derivatives. Okay, one announcement to make before we start the session. I want to remind you that the homework assignment for this week is due on Sunday. That is March 30 at 11 p.m. Also want to remind you that the next class exam, that is exam number 3, is scheduled for April 8th. Okay, that's about less than 2 weeks from today. Okay. Okay, if you recall when we left on Tuesday, we were discussing the synthesis of esters, and I believe I gave you 2 synthetic methods, and I believe this, what you have on your screen now, was the second method I gave you. So I will say method number 2 under the synthesis of esters. Okay, so I will call this SN2 reaction involving carboxylate ions carboxylate ions and alkylating agents. Okay, now what do we mean by this? Anytime we have a carboxylic acid, and if you remove this proton here, this hydrogen that is attached to oxygen, through some acid-base reaction, what you obtain here, the conjugate base is what we refer to as the carboxylate anion. In other words, an anion coming from the carboxylic acid. So that is the conjugate base of the carboxylic acid. So we refer to this as carboxylate. Okay. So this example here, we are using a carboxylate ion, and then of course the alkylating agent here is this methyl iodide. Keep in mind, since this is an SN2 reaction, the alkylating agent must be that in which the leaving group must be attached to either a primary carbon, a methyl carbon, or a secondary carbon. You cannot use a tertiary carbon for SN2 reaction, so keep that in mind. So anyway, so here we have an SN2 reaction. The anion acting as a nucleophile, displacing the iodine, and then we have the product here, which is methyl. Okay, methyl butanoate. It is methyl butanoate because this is the ester of butanoic acid. Okay. And keep in mind that the name of the ester is derived from the name of the corresponding carboxylic acid. In this case, the corresponding carboxylic acid is butanoic acid. And what do we do? To get the name of the ester, we remove the last IC, and then we remove the word acid, and we replace with ATE. And that is what you have here, butanoid. Okay, and also notice here, the name of the alkyl group that is attached to the oxygen must be a separate name. Okay, so these are separate words, methyl butanoid. Another example of this, you could have this. I could have this here. React with sodium hydroxide in order to form the carboxylate anion. I say step 1, and then step 2, I could add the alkylating agent. Say, for example, I want to use a secondary alkylating agent, cyclohexyl iodide, and then I will get this here. Okay, so what would be the name of this ester here? What would be the name of this ester? Cyclohexyl benzoate. Very good. Cyclohexyl, one word, and benzoate. Because this is an ester of benzoic acid. This is benzoic acid here. Okay, so that is method number 2 for making esters. Then we have method number 3. Still the preparation of the synthesis of esters continued. Okay, as a matter of fact, I think I do have that on my PowerPoint slide here. Okay. Method number 3. So I will call this acid catalyzed synthesis of ester, or acid catalyzed esterification of carboxylic acid. And this we refer to as a Fischer esterification. In this case, what do? We take a carboxylic acid and we take an alcohol. Generally, we use very low molecular weight alcohols in the presence of some acid catalyst. In this case, we are using hydrogen chloride. Very often, we use sulfuric acid or phosphoric acid. So under acid catalyzed condition, then we get the ester. So we call this acid catalyzed esterification, because the process of forming an ester is what we refer to as esterification. Okay. Another example of this could be do that in the presence of some catalytic amount of sulfuric acid, for example, and then we obtain this. Okay. So what I want to do, I want to give you the mechanism of this reaction. Okay, in this particular instance, let us take a look at this here. Let us consider this part of the molecule. I want to use a generic carboxylic acid. Consider that that is an R group, okay? Or this part also could be your R group. Sorry. Or this could be your R group, okay? Just to make things easy for ourselves at this point. So what I want to do here, I want to use a generic carboxylic acid. The first thing you do, you have your carboxylic acid, and since we are using catalytic amount of acid, what happens here, consider this as source of a proton. The non-bonding pair of electron on oxygen, start this, let's do this, make it proper. Keep in mind, in this case, we are using very small amount of water in the system. Generally, we use a very concentrated acid. Okay. Okay, once we do that, we protonate the oxygen, just as most of the reactions of carbonyl compounds that we have been dealing with. So now we obtain it. By the way, this will be an equilibrium reaction. Okay, that oxygen is now positively charged. Now the purpose of this protonation of the carbonyl oxygen is to make this carbon here a lot more electrophilic, because once you protonate the oxygen, the pi electron will be drawn towards the oxygen, thereby making this carbon here positively charged. So now you could now have your nucleophile. This time, let us use methanol or any alcohol, whatever the alcohol that you want to use. Okay, so the non-bonding pair of electron on the oxygen on the alcohol, in this case methanol, will act as a nucleophile, will attack this here. Pi electron goes to oxygen.
I'm sorry,
Yes.
question. Since should have double error. We use the same reagent to go from acid to carboxylic acid.
Yes, yes. When we get to the end of this process, I will make that point. Yes, it's a very good point, though. Okay, so we have this. Now we have this here. Now you have, when you draw the reaction mechanism, you need to account for all of your electrons. Okay? Okay, and all of your atoms also. So now we have okay, so that means this oxygen here is positively charged because it is the oxygen here is using a pair of electrons to bond to the carbon, so therefore it is positively charged. Okay, so now the next thing that happens, we are going to have what we call an internal acid-base reaction, or intramolecular acid-base reaction, in which we are going to transfer this proton to this oxygen here. So this pair of electrons here will grab the proton here and releasing this pair of electrons to oxygen. So now we have and the positive charge is now transferred to this oxygen. So now this molecule is now set up to lose water, because as you know, water is a very good living group, very stable molecule. So what do we have? We have this will leave. And in so doing, we'll be creating a positive charge on this here, so we are going to form a pi bond between that oxygen and the carbon, and then we get this here. Let me use this here, use this space right here. It's a long. So now we have this. Positively charged, and now we have now we have this water here, the water that we release right here. Okay. So finally, that water will simply now come in to relieve this proton, this oxygen of the proton, and thereby releasing the electron to oxygen here. Okay, so now we have plus the hydronium ion here. Okay. Okay, so now that is the reaction, the mechanism for the generation of your ester. Now, if you also notice here, just as Kiara told us earlier, this here, if I gave you an ester and I ask you to give me the mechanism from ester to carboxylic acid, which is going from here to here, you notice this is the reverse, the hydrolysis of an ester to carboxylic acid. The mechanism is the reverse of the acid catalyzed esterification. So you simply just have to go backward. Okay. Of course, the first thing is protonation, and then once you protonate, then the water attacks, so then goes all the way back. Okay. You follow that? Okay. Anyway, this is a very important reaction because I'm sure most you guys have already done this in your lab already. Did you do esterification? Okay. Very good. Okay. So. So now, so far, we have given you three methods for making ester. One method is from the carboxylate reacting with an acid chloride. The second method is carboxylate reacting with an alkylating agent, a primary alkylating agent or secondary alkylating agent. And then the third method that I've given you is the acid catalyzed esterification of carboxylic acid using alcohols. Okay. Now, the last of the carboxylic acid derivatives, the synthesis that we want to discuss is synthesis of amides. Okay, of course, amides are this here. You have the Acyl group attached to, this case, an amino group. This we call a primary amide. We could also have a secondary amide. Because it's a methyl group here. In which case, in the secondary amide, the nitrogen is attached to 2 carbon atoms. On the other hand, in the primary amide, the nitrogen is attached to only 1 carbon atom. Okay, and so this is your secondary amide. And finally, we could also have a tertiary amide. In which case the nitrogen could be attached to any alkyl group. Okay, no hydrogen attached to the nitrogen. Here, the nitrogen is attached to 3 carbon atoms. Now, so how do we make this? We make this from nucleophilic acid substitution. Okay, I will say nucleophilic acid substitution reaction of acid chloride with ammonia or amines. Okay, now let's look at a specific example. We take this here. We have this acid chloride here. And we could react this with ammonia from this. Now to name this molecule here, well, let me give you a simple example before we get to this. So we get this here, ammonia reacting with this acid chloride to get this here. Now it also react with this butanoic chloride to get this amide. Now to name this amide, the name of the amide comes from the name of the corresponding carboxylic acid. Whenever you are dealing with a straight chain amide, okay, it's called straight chain amide. So in this case, the corresponding carboxylic acid here be coming from this 4-carbon molecule here. So that would be butanoic acid. So what do? We remove the OIC or IC of the corresponding carboxylic acid, and we replace with the word amide, one word. So therefore, to name this molecule here, this becomes butane amide. Become butane amide. Now supposing in this case we call this here a primary amide. Okay. Now supposing we want to make a secondary amide. Use the same acid chloride. To use a secondary amide, what to do, instead of using ammonia, you use a secondary amine. I'm sorry, you use a primary amine, sorry about that. Use a primary amine. A primary amine is that in which you have the nitrogen is attached to only one carbon atom. Use a primary amine. Then you obtain this. Now, how do we name this? Once again, the name is derived from the name of the corresponding carboxylic acid. So to name this here, what you do, you have the base name will be butane amide. Okay. So now, because you have the ethyl group attached to nitrogen, so you have to do this. Say N ethyl, that is, the ethyl is attached to nitrogen, N-ethyl, then you give the base name, butane amide. Butane amide. Okay, one word. N-ethyl butane amide. Now supposing we want to make, so this is a secondary amide. Now supposing we want to make a tertiary amide. Let us take the same. To make a tertiary amide, okay, you take your acid chloride, and this time you take a secondary amine. Let's say we have this here. You notice here the secondary amine you have nitrogen is attached to 2 carbon atoms. So you obtain this. Now, how do we name this one here? Okay. Once again, the name comes from the corresponding carboxylic acid. The base name is a butane amide because you have in the corresponding carboxylic acid, you only have 4 carbon atoms right here. So now to name this, you look at the alkyl group that are attached to nitrogen, and you give the name in alphabetical order. Okay, so you have ethyl and methyl, so this becomes N-ethyl, N-methyl, butane amide. Supposing you have this here, a molecule that has this here, in this case, even though this is a tertiary amide, the nitrogen is attached to the same alkyl group, okay, 2 methyl group here. So to name this here, you simply say N, N dimethyl. Then you give the base name. This time the base name is, what is the base name? Propane amide. Very good. Propane amide. Okay. Okay, so now we've given you a method for making all of the 3 different types of amide. Okay, there is one more method I want to give you. Okay, reaction of amines with carboxylic acids in the presence well, let's say with catalytic amount of, well, let's say, okay, in the presence of dicycloacyl carbodiimide. And this molecule here, we give the acronym DCC. So for you in the future, just simply write DCC. This for D here, C for the C here for cyclo, and then this carbodiimide, DCC. And this is this molecule here. So you don't need to write that molecule. That is the molecule DCC. Now, what do? You take carboxylic acid. Okay, you could take ammonia. Okay, in the presence of DCC. Gives you, so here you could go directly from the carboxylic acid to the amide. What happens here, ordinarily we tell you that the hydroxy group is not a good leaving group, but what happens, this hydroxy group combines with the DCC and becomes a good leaving group. Okay. Okay, you could also use another example here. You could take a primary amine, presence of DCC, okay. You also make a tertiary amine. In this case, you have make a, this is a secondary amine, secondary amide. Okay, you could also make a tertiary amide. Use the same acid. This time, take a secondary amine to start with. DCC. Okay, so those are the two methods for making amides. Now, at this point, we want to go to the reactions of carboxylic acid derivatives. Now, before we give you the reaction of carboxylic acid derivatives, I want to give you the order of reactivity of all of the carboxylic acid derivatives that are of interest to us. We have the acid chloride. This is the most reactive. Then followed by the anhydride, and that is more reactive than the ester. And the ester is more reactive than the amide. Now what this means is we could obtain all of these other derivatives from the acid chloride. Now here we could obtain all of the esters and the amide from acetic anhydride and also from the acid chloride. Now we could obtain the amide from the ester, from the anhydride, and from the acid chloride. But the anhydride cannot give us the rest of these carboxylic acid derivatives here. So this is the most reactive and this is the least reactive. Okay, keeping that in mind, let us now begin to take a look at the reactions of this class of compounds. What I want to do, I want to start with the amide, and then from the amide we want to go to the acid chloride. Some of this we've done before. If you recall, if you take this amide here, remember when we did nitrile, if you take the amide, to react the amide with thionyl chloride, and you get a dehydration. This case you get cyclohexane carbonitrile. You could also take the amide, hydrolyze, dilute acid to get carboxylic acid. Keep in mind, this is a general reaction here. This applies to any of the amides. We could also take this, either a primary amide, this is a case of a primary amide. We could also do this on the secondary amide or tertiary amide. Take lithium aluminum hydride, followed by hydrolysis. What this will do is to transform the carbonyl of the amide to a CH2. In this case, we get a primary amine. Keep in mind, amine is different from amide. Okay. Okay. So what does the lithium aluminum hydride do? We take the carbonyl of an amide and transform to a CH2. Okay. So these are the three reactions of amide that I want to at least I want to give you for now. So let us go to reactions of acid chloride. Since the acid chloride is a lot more reactive, get more reactions from the acid chloride. Okay. Let's take this here. Even though I am using a specific example, this will apply to all of any acid chloride, okay? The acid chloride will react with water, dilute acid, to give you, sometime in this particular instance, just water alone you might be able to do this reaction with just water without the acid catalysis to get carboxylic acid. To also react with a Gilman reagent, remember the Gilman reagent. Let us imagine that we have this Gilman reagent here. To react with a Gilman reagent to give you a ketone. This is also will apply to any Gilman reagent with acid chloride. And as I told you earlier, you can use this here to go to any of the other derivatives to react with alcohol to give you an ester. You could also react with a carboxylate ion. Okay, for example, here we have this here. We react with that to give you anhydride. And of course, you know, based on what we just discussed with regard to the amide, it will react with the amines to give you the different types of amide. So let me just give you one example of that. So you can see here the acid chloride is a very useful synthetic starting material. To react with any of the amines to give you the corresponding amide. Okay. So at this point, I believe I want to start with the reactions of acid chloride and then give you the mechanism of this reaction. Because all of these reactions come under the class of reaction mechanism that we refer to as nucleophilic acyl substitution reaction. Okay. Nucleophilic acyl substitution reaction. Okay, what I want to do, I want to use the acid chloride reaction as an example. Let's take, for example, this reaction here. In case in which we are using this amide, this amine. All these reactions are basically the same. They are basically the same type of reaction mechanism. Okay. So what is the mechanism of this reaction? What is the first thing that happens? Start with the acid chloride. Because of the reactivity of the acid chloride, in this case, it does not need an acid catalyst. It could react directly with the nucleophile by itself. So we have this here. Okay, so the first thing that happens, the nitrogen, the lone pair of electron on nitrogen act as a nucleophile attach this carbonyl. This pi electron goes here. Okay? And then we have this. It's a very rapid reaction. Keep in mind we have non-bonding pair of electrons here to start with. So now we have this. We have this tetrahedral intermediate. Of course, the nitrogen will be positively charged, so called tetrahedral intermediate. Okay. Now what happens at this point, we are going to reform the carbonyl. And so once we regenerate the carbonyl, chloride will leave. And then you have this. Okay. Of course, now the chloride is here. So this chloride simply just comes here and grab the proton. Drag the proton away from the nitrogen, and then this will release the electron to nitrogen. Okay, so that's how you form your HCl right here. Okay, so what we've done, what have we done here? What we have done, we have replaced the chloride with the amine group, and so that is why we call this nucleophilic acyl substitution reaction, because the reaction is taking place on the acyl carbon. This is the acyl carbon here. We are substituting the chlorine that is attached to the acyl group with some other group. So most of the reactions of this class of compound, they come under this type of mechanism. Okay, and the same mechanism for all of them. For example, I told you that you could take hydrolysis, you could hydrolyze this to carboxylic acid, right? Let us use a generic acid chloride. If I take this and I take water, what does it do? Just like the ammonia does. What does it do? What is the first thing that happens? What is the first thing that happens? No, oxygen attacks, very good. Oxygen attacks the carbon. It's the same mechanism. Okay, so you form your tetrahedral intermediate. Okay, and then what happens next? What happens next? You reform the carbonyl, very good. See the same mechanism. And then the chlorine will leave. And then you have this. Of course, the chlorine is here. And so the chlorine just comes here, just grab the proton. Okay, so all of these are basic, they are all the same reaction mechanism. And that is why we call them all nucleophilic acyl substitution reactions. Okay, the same thing when the Gilman reagent reacts with them. Keep in mind the Gilman reagent, let us say we have this here. So think of this Gilman reagent here as nothing but a source of and that's your nucleophile. That's the nucleophile that will attack the carbonyl carbon. And then everything happens from there. Okay, so all of these reactions that we just given you, they come under this category of reaction mechanism, nucleophilic acyl substitution reaction. So at this point, what I want to do, I want us to do some problems. Okay, let's spend the rest of the time to do some problem. And also, I do have some of your old quizzes here, so stop me about 5 minutes to the end of class, so I'll give this to you. Okay, let us see here. So let us see whether you understand everything that we've discussed so far. So by doing some problems. Okay, Jasmine, can you go ahead and read this for us?
Write the major organic product for each of the following reactions.
Okay, thank you. Okay, write the major organic product from the following reactions. Some of this we've done before. Okay, so what do we have here? What class of compound is this? An ester, okay? This is an ester. Keep in mind, sometimes when we have ester, we, instead of doing this here, writing it out, we could simply just do this. Okay? Okay, so this is an ester. Okay, so an ester reacting with a Grignard followed by hydronium ion. What does it give you? A tertiary alcohol. Exactly. Excellent. So this time we have two types of mechanism taking place. The first type of mechanism is the nucleophilic acyl substitution reaction. Because if you recall, when we did this, you form a ketone intermediate. Okay, once the Grignard first reacts with the ester, you form a ketone intermediate, and that ketone intermediate now reacts with another Grignard to give you your tertiary alcohol after you add the dilute acid. So from here to here, this is your nucleophilic acyl substitution reaction. And here, going from the ketone to here, remember the mechanism for that is nucleophilic addition reaction. Remember? Okay, so this is nucleophilic addition reaction. Because the nucleophile here simply adds to the carbonyl. Okay? Here, the nucleophile replaces something on the carbonyl. Okay? Okay, so therefore, what is the product here? You follow that? Without me having to go through the mechanism, we don't need to do that again. Okay, because the first thing that happens, if you recall, go back to your notes, the Grignard will react with an ester, gives you a ketone intermediate, then the Grignard continues to react with it to give you a tertiary alcohol. Okay, so let us see here, what is the product? So the product for this here, let us look at it. This is cycloacyl group. And the ester, so we have this here. Okay, so then we have the two ethyl group from the, keep in mind when you react the Grignard with the ester, two alkyl group from the ester will now be joined to the carbonyl carbon, and that is what you have here to form a tertiary alcohol. Because this part of the molecule here, this part of the molecule will be gone. Let me write it out so that, remember the starting material is this. This part of the molecule will be replaced during the nucleophilic substitution, okay? And then the other part here will now come in during the nucleophilic addition reaction. Okay, very good. About C, what are we doing here? What class of compound is this? Acid chloride, okay? Acid chloride with amine, primary amine, what do you get? Secondary amide. Okay, very good. Okay, so this part here, this is this here, and this is this part here, okay? Okay, these are, of course, you know, this is nucleophilic acid substitution reaction. About here, E, what is going on here? What class of compound is this? Ester, very good. What happens ester reacting with a lithium aluminum hydride? What do you get? What do you get? We did that before. You get a primary alcohol. Once again, two types of reaction mechanism. The first reaction mechanism is nucleophilic acid substitution. In this case, you are using the hydride. Using the hydride for the first part, nucleophilic acid substitution, that will substitute the alkyl group that is attached to the alkoxyl group. And then the next time, keep in mind you form an aldehyde. So here, the first thing you get an aldehyde intermediate. And then the next step, you get the primary alcohol. Okay, let me write that better than that. So okay, this part here, this is the nucleophilic acid substitution reaction. And this part, this is the nucleophilic addition reaction to carbonyl. Okay, so there are two types of mechanisms taking place here, and in this case, the reagent, whenever you have lithium aluminum hydride, is this here. Okay, so just the mechanism that I gave you earlier with nucleophilic acid substitution, just use hydride if I ask you for this mechanism. Instead of the amine or instead of the water, just use the hydride. Okay, from the aldehyde intermediate, and then another hydride attached this here, nucleophilic addition, and then when you add the water at the end, that is where this comes from. This here comes from the water. Okay, okay, very good. Now let us do the last one. Okay, the last one here, you have a primary amide reacting with lithium aluminum hydride. What do you get? Okay, primary amine. This here, this carbonyl becomes a CH2. Okay? So do not forget what we told you earlier. So those are the, like I keep telling you, those reagents, those are the ABC of organic chemistry. You need to know them. So this here, this is this compound here, this right here. And then with lithium aluminum hydride, LAH, followed by dilute acid, get this here. Okay, very good. Okay, so let's do the next one. Notice here, carbonyl becomes a CH2. Okay, well, there's no caption here, so we'll just give the... Hopefully, can you just give me a title here? Just give me a title for this reaction here, yeah, a caption for this. Assume you are the instructor. Okay, Product, exactly. Okay, exactly. Give the, give the products of the following reaction. Very good. Okay. Okay, here we're starting with an ester with dibol. What does that give you? Dibol with an ester. What does it give you? Remember, you guys are forgetting. You need to remember all your reagents, all your reactions. An ester with dibol gives you an aldehyde. Very good. Very good. Ester with dibol gives you an aldehyde. Okay, and this is another example of nucleophilic acyl substitution, because all you've done is to substitute the alkoxy, this part of the molecule, all you've done is to substitute this part of the molecule with this here. That's what you've done. So therefore, the dibol is a source of hydride. So if I ask you for this mechanism, just use the hydride, and then you do your nucleophilic acid substitution reaction. Okay. About D, what are we doing here? What do you expect to happen here? Acid catalyzed esterification, which is Fischer esterification. Very good. So we are reacting the carboxylic acid with methanol. So you expect to get an ester. Okay? And don't forget the stereochemistry here, so you still preserve your stereochemistry. And believe it or not, this is also an example of nucleophilic acid substitution reaction. Keep in mind, what you have here is you are starting with a carboxylic acid. So what have you done? You replace the hydroxy that is attached to the acid group with this here. Okay? So if you know the mechanism I gave you for the esterification of carboxylic acid, that is also another example of nucleophilic acid substitution reaction. Okay? Okay. About this here, F. We do this couple and then we call it a day. Okay. About F. An alcohol, what class of compound is this? This is anhydride. This is anhydride, okay? Okay. It's actually this here, CH3, this here, this here. That's acetic anhydride. So acetic anhydride reacting with an alcohol, what does it give you? It gives you an ester. An alcohol reacts with an hydride to give you an ester. So you get this. This time you get and believe it or not, this is also an example of nucleophilic acid substitution reaction. What are we doing here? We are replacing this part of the molecule, this becomes a living group, with, we are replacing with this here. Okay, that's all we've done. So that is also an example of nucleophilic acyl substitution reaction. And finally, okay, we are going from a carboxylic acid reacting with styrene chloride. What does it give you? acid chloride. And that will be the end of today's session. Okay, carboxylic acid reacts with a thionic chloride to give you an acid chloride. Okay. Okay, so I will give you back your quizzes, and on Tuesday we are going to have a short quiz on Tuesday. So enjoy your weekend.